Hello guys, Serge here, and today we are doing the second video for the series of rewriting physics. What we're going to talk about today is again in EM physics, the magnetic field, and we're going to be talking about the electric and magnetic fluxes along with their length-based counterparts, that would be viscosity and momentum. So with that being said, let's get started. We would first like to look at force equals QV cos B, the usual magnetic field formula. Well, one of the normal electric field formulas. Then we can find that force is viscosity times area times the speed of the fluid per the separation of plates. So purely mathematically, completely ignoring the facts that velocity is a vector and that we can't divide by vectors, we will pretend like we can and just divide. Or what we can do is just say that none of these are vectors and that velocity is just perpendicular to the magnetic field. But either way, unit-wise, it still creates the same thing. It'll still create a magnetic field. And here we can solve for the viscosity. So that'd be A U over Y. And U again is a speed, so I will actually replace that with a V here. And that will be a mu. And after doing a bunch of math, a bunch of SI unit math, we find that the magnetic field has units of kilograms times coulombs per second. And that viscosity has units of kilograms per meter second. Editor here, I decided I would go a little bit more in depth into the SI units. So with that being said, let's look at the SI units for the magnetic field. If I can write instead of erase. Force equals, force per charge velocity equals magnetic field. Mathematically, at least. Firstly, we look at force, and that is kilograms times meters per second squared. Then we can divide that by force, that's coulombs. And multiply by velocity, that's meters per second. Again, the meters cancel out. This cancels. And you get kilograms per seconds coulomb. If we look at viscosity, so that would be F Y over AV. I would first like to note that A over Y is just a length unit-wise, but we'll go through all the steps anyway. So kilograms times meters per second squared, and then Y is meters. A is area, so meters squared, times meters per second. And again, these meters cancel out. This 2 cancels this meters out. And then this seconds cancels this out. And we get kilograms times seconds meters. All right, that's the analysis we have there. But anyways, back to the main content. And again, all we have to do to get from the magnetic field to viscosity is replace coulombs with meters. What does this mean for our notation? Well, we'll recognize that there's no meters in the charge-based magnetic field. Thus, we can just define our B as having units of kilograms per unit seconds. And thus, we find viscosity can be denoted as B by length. Now, I think I should probably include a few formal definitions. Last video, we kind of just skimmed past the formal definitions and just said that we have a charged form of force or a charged form of energy or whatnot. But here we need to make a formal definition because we are going to be using this for the rest of our notation. So each of these letters will be called a subquantity. The formal definition of a subquantity would be a physical quantity whose SI units change depending on whatever quantity it depends on, which is going to be denoted as epsilon if we're looking at a general quantity. So with that being said, we found the magnetic field. Let us now check out the different fluxes. We will first go back to last video and look at the electric field. So the electric field was gamma 1Q, and voltage was dL. We already kind of know this is force of charge. But we'll go through this process just to see how we can figure out the units that we have. So gamma is specifically kilograms times seconds squared, and 1Q means that we multiply these SI units by meters per coulombs, in this case, to the first power. And if we are integrating by length, we want to square this. So with that being said, we can go squared and then multiply by coulombs. This definition will end up giving us force of 2Q. Oh, well, it's integrated, so it doesn't need, never mind, doesn't need a vector mark. But this will end up giving us force of 2Q, and that is our voltage. Now let us look at electric flux. And remember, the definition for electric flux is just the integral of the electric field integrated over area. And the reason I cross my D's is to differ the D's from distance. So don't worry about that. That's just a special little thing I do. That will be energy 3Q. And the way we can figure that out is, again, look at the units. Kilograms times meters per second squared coulomb. And we want to integrate by area, so that means we get meters cubed per second squared coulomb. And one way to write that, well, the way to write that by canceling out all the meters. Kilograms times coulomb squared per second squared. Meters per coulombs cubed. So with that being said, we should probably also explicitly mention the SI units for force and energy. We have just kind of brushed over them, but let's formally define them. Force has SI units of kilograms times the unit per second squared, meters per the unit to the n, and energy is kilograms times the unit squared per second squared, meters per unit to the n. Well, energy in U. There we go. Now let's finally look at the magnetic field. So we'll be looking at the magnetic field integrated by length, the magnetic field integrated by area. Remember, the magnetic field is kilograms per coulomb second, so actually we don't really need to change the color. Kilograms by coulomb seconds times meters, we get kilograms per second, meters per coulomb. Sorry for the messy writing, but as defined before, that should be a 0Q, by the way. As defined before, we can recognize this as resistance with 1 as a power. And we can then go with kilograms times meters squared by coulomb seconds. And again, we want to remove the meters. And here we would like kilograms times coulombs per second, meters per coulombs squared. And here, this will actually end up becoming momentum. So I should actually mention that this is the magnetic flux. I'll put a tilde over this P in order to not confuse it with power. So that'd be P2Q. So this ends up comparing itself to momentum. So with that being said, the last thing I would like to look at is the derivative of the electric field over time. As of right now, it doesn't actually have a value. And it looks like in my current notes, it doesn't have a value either. But we'll still look at this. Yeah. These units will be kilograms per second squared times meters per coulomb, and this becomes seconds cubed per coulomb. Replacing coulombs with meters, that goes away, and we're left with what I would consider a jerk of mass. And jerk for reference is just the derivative of acceleration by time. Well, we can define jerk as the derivative of acceleration. So d alpha by dt, which means it has the units of u per seconds cubed. This just seems to be the jerk of mass times some other density. Times the, over the charge density, I'm sorry. That'd be over the charge density. I will go ahead and talk about the integral of the electric field by time. I have started to notice its importance. We get kilograms per second squared times meters per coulomb. So kilograms times meters per second is resistance. Okay. But we'll notice there's some repetition in notation. That's why that's why I will commonly write a letter as a superscript to show what this value comes from. So let us do that real quick. Gamma and B. And we will also define one last object, and that is the Poynting vector, of which is the electric field cross the magnetic field over 2. Unit-wise, we find the electric field is kilograms times meters per second squared coulomb. Magnetic field is kilograms per seconds coulomb. And thus the official definition of S in SI units, kilograms squared times meters per seconds cubed coulomb squared. And in order to completely remove meters from the equation, we can define it this way. So with that being said, S's official SI units, when generalized, will be kilograms squared per seconds cubed coulomb, meters per coulomb to the n. Not coulomb, but the unit. Now, if someone is able to find a representation of this in length, please let me know, because I will be for sure fascinated by it. Editor Ert here, I have decided to share another consequence of the Poynting vector, and that is I will define a separate S tilde to have units of just kilograms per seconds cubed times the unit, and then obviously meters per the unit to the n. And the reason this is necessary is because the magnetic field is kilograms per seconds u, and that means we get the second derivative of the magnetic field, of which, if you didn't know, is used in the formula for light waves. If you don't know if your formula is correct, always check your units. Anyways, we can now represent at least half of this formula in our notation. With that, we get S tilde vector. I'm sorry, that is slightly messy, but because this is 0q, S also stays 0q times the speed of light, so v of light. And then all we need is the second derivative of the electric field, of which sadly doesn't have a notation, but if we're using, I think it's Newtonian physics, we can just go with gamma dot dot for now. But technically, I guess we can kind of write that. It's not my favorite way of denoting it, but that works. So that is the new version of the light waves formula. So with that being said, let us get back to the video. Next video, we will be looking at permittivity and permeability, and possibly the displacement fields and also a little comment. Something else that I wrote in the last video that I really kind of glossed over was frequency. I am using F with the tilde to represent it. Uppercase or lowercase doesn't matter. But F with the tilde is frequency, which is just 1/seconds times meters per the unit to the n. So that's hard. So with that being said, thank you so much, and I will see you in the next video. Bye, everyone.